When you think about scientific revolutions, certain names just pop into your head, right? Einstein, Newton, Galileo, even Da Vinci in his own way.
Absolutely. Figures who didn't just tweak our understanding, they fundamentally changed how we see the universe itself.
Exactly. And that brings us to today's deep dive. We're looking at some really interesting material proposing a new idea, motion theory. And the question really is whether this theory could potentially be considered in that same kind of revolutionary context.
It's a huge question.
It is. And let's be clear, this isn't about crowning someone a genius. It's about looking hard at the impact an idea might have.
Right. And to do that, you first have to appreciate the scale of what those giants actually did. Take Newton.
Okay.
Before him, you had apples falling and planets orbiting. Two totally different things in people's minds, governed by different rules.
Right. Celestial and terrestrial, separate domains.
Exactly. Newton comes along and says, no, wait. His universal law of gravitation, his laws of motion. They explain both. Suddenly, the universe is this understandable mechanistic system.
That really was the birth of modern science, wasn't it?
Pretty much, yeah. He gave us the mathematical tools, the framework.
And then fast forward a couple of centuries, and you get Einstein.
Who doesn't just build on Newton, he kind of turns the tables again.
He really does.
Yeah.
Space and time aren't separate stages anymore.
No, they're woven together, this dynamic fabric, space-time. And his theories, special and general relativity, well, they completely rewrite gravity, motion, energy.
Leading to things that sounded absolutely bizarre at first. Black holes, light bending around stars.
Things we've now observed, which is incredible. So that's the kind of benchmark we're talking about. Does motion theory propose something that fundamental?
That's the core question for this deep dive. Does it represent a similar kind of paradigm shift in how we understand reality?
Okay, so motion theory, its central idea is, well, it's quite a leap from the standard model of physics.
How so?
It basically proposes that everything, and we mean mass, gravity, energy, maybe even consciousness, isn't ultimately made of tiny particles interacting in space-time.
Okay. So if not particles in space-time, then what?
It's all proposed to be a manifestation of structured rhythmic motion.
Structured rhythmic motion.
Yes. Which immediately suggests that maybe particles, waves, even space-time itself, maybe they aren't the bottom layer. Maybe they're emergent properties of this underlying motion.
Okay, that's a big claim. Structured rhythmic motion. Let's try to unpack that a bit. How does it redefine concepts we think are pretty solid, like mass?
Right, mass. We usually think of it as, inherent stuff, how much matter something has.
Yeah, it's intrinsic property.
Motion theory reimagines it completely. It defines mass as motion resistance.
Motion resistance.
Yeah. So the idea is the more complex and stable the underlying pattern of rhythmic motion is for something,
Okay.
the harder it is to change that pattern. That resistance to change is what we perceive and measure as mass. It's not about the stuff. It's about the stability of the motion structure.
Huh. That's a very different perspective. So, particles then. If they aren't tiny balls of stuff, what are they in this view?
They're described as stable, repeating loops of motion synchronization.
Loops of synchronization.
Imagine incredibly complex, self-sustaining patterns of vibration, almost like knots of rhythm that hold themselves together. What we detect as a particle is one of these stable, synchronized motion patterns.
Okay. And gravity. Newton's force pulling things together. Einstein's curvature of space-time. What does motion theory say?
It sees gravity not as a force or even space-time curvature in the usual sense, but as structured motion naturally converging toward higher synchronization densities.
Convergence.
Density. Think of it less like a pull and more like, well, a tendency. These complex motion patterns naturally tend to move towards regions where the motion's already more concentrated, more synchronized.
So denser areas of synchronized motion sort of draw in other motion.
That's the idea, yeah. It leads to the effect we call gravity, but the underlying mechanism is proposed to be this synchronization dynamic.
Wow. Okay, that's a major shift. What about time? That feels about as fundamental as it gets.
We experience it as this forward flow, right? Constant, universal.
Yeah.
Motion theory reframes time, too. It suggests time is a local rhythm resolution rate.
Local rhythm resolution rate.
Yes. So it's not this universal clock ticking everywhere. It's more like a measure of how quickly the rhythmic patterns within a specific system are cycling, interacting, resolving. Time becomes an outcome of the activity, not the background stage.
So time could actually tick at different rates in different places based on the local motion activity.
Potentially, yes. It's a local property derived from the motion itself.
This feels like it touches everything, even just seeing things.
Yeah.
Vision. We think light hits our eyes, right? Photons.
The standard view, yes. Photon absorption triggers signals. Motion theory offers a nuance there.
Okay.
It suggests vision isn't just about absorbing photons. It posits that our visual system actually evolved to detect rhythmic synchronization patterns in the incoming energy.
So we're detecting the underlying motion patterns, not just the light particles.
In essence, yes, we're perceiving the universe's rhythmic structure directly through these patterns.
Okay. So if Einstein unified space and time, it sounds like motion theory is trying to unify, well, almost everything else under motion.
That seems to be the ambition, yes.
Yeah.
It aims to connect phenomena characterly. We usually keep separate gravity, electromagnetism, quantum mechanics, and suggests they all arise from these underlying dynamics of structured motion.
And maybe even biology, consciousness.
That's part of the proposal, too, that synchronization dynamics might be the key to understanding biological processes, maybe even the emergence of consciousness itself. It's trying to provide a single, fundamental principle structured motion for everything.
So if we think about Newton connecting the apple and the planets, and Einstein connecting space, time, gravity, and energy,
Right.
motion theory seems to be suggesting an even broader unification, potentially encompassing physics, chemistry, biology.
That does seem to be the scope, yeah.
Eh.
It's incredibly ambitious, trying to find this common root in synchronization dynamics across all these fields. Potentially, yes, its scope aims even broader than Newton or Einstein.
Ambition is one thing, though. Explanatory power is another. A truly great theory needs to elegantly explain what we already observe, maybe even solve some puzzles.
Absolutely.
How does motion theory handle the really weird stuff, like quantum mechanics? That was famously tricky even for Einstein.
Right, the skooky action and all that. Well, this is where motion theory claims to offer some elegant solutions. Take quantum tunneling.
Okay, particles going through barriers they shouldn't be able to cross.
Exactly. Instead of a particle somehow magically appearing on the other side, motion theory describes it differently. Remember those stable loops of motion?
Mm-hmm.
Tunneling is seen as these motion loops finding a way to transition their synchronization state across the barrier. It's like the rhythmic pattern finds a resonance that allows it to propagate through rather than the particle itself passing through.
And entanglement, that instantaneous connection between particles no matter the distance.
Motion theory explains that as extended synchronization across structured motion systems.
Extended synchronization.
Yeah. The idea is the two particles were part of the same synchronized system from the start. Their connection isn't information traveling faster than light. It's that they remain correlated parts of one larger underlying rhythmic pattern. Changing one affects the whole pattern, including the distant part.
Okay. What about the classic double-slit experiment? Particle or wave, depending on observation.
Motion theory suggests the particle, that motion loop interferes with itself, its own rhythmic pattern, creating wave-like interference as it propagates.
Until you look.
Until you detect it. The act of detection forces a synchronization event, collapsing the spread-out pattern into a specific, localized state that we measure as a particle landing in one spot.
It provides a mechanism, then, for observation collapsing the wave function.
That's the idea, yes. The interaction forces a resolution of the motion pattern.
And even something more applied, like superconductivity, zero electrical resistance.
Motion theory offers a simple picture. Perfect synchronization of electron loops. When the motion patterns of the electrons achieve this perfect collective rhythm, they flow without the scattering and disruptions that normally cause resistance.
These are definitely elegant ways to reframe these quantum mysteries. But is it just reframing? Is there any experimental evidence pointing this way? Anything that supports this structured motion view?
The material we looked at points to a couple of things. One is the quantum Zeno effect.
Where observing a system stops it from changing.
Exactly. Motion theory interprets this as a synchronization lock. Continuous observation keeps interacting with the system's rhythm, preventing it from naturally evolving or transitioning to a new state. It fits the synchronization idea quite well.
Okay, that's interesting. Anything else?
There's also mention of recent advanced optics experiments. These apparently lend some support to the idea that vision does rely on detecting rhythmic synchronization patterns, not just photon counts.
So potential hints in both quantum physics and biology.
That seems to be the suggestion, yes. Early days, perhaps, but potential corroborating evidence.
It's also worth remembering, isn't it, that big new ideas in science almost always face pushback.
Oh, absolutely. History is full of it. Think of Copernicus suggesting the Earth wasn't the center of everything.
Right. Or Galileo getting into trouble for backing him up with telescope data.
Even Einstein faced skepticism initially. General relativity was complex, counterintuitive, paradigm shifts, challenge, established thinking, established careers, everything. So resistance to motion theory wouldn't automatically mean it's wrong.
It's almost part of the process for truly revolutionary ideas.
You could say that. Rigorous skepticism is healthy, it's necessary for science, but it doesn't negate potential.
So for motion theory to gain wider acceptance, what needs to happen next? What are the crucial steps?
Well, the material lays out a pretty standard but essential path. First, more rigorous experimental testing. The predictions need to be tested, refined, maybe new predictions made and checked.
Makes sense.
Second, it needs a really solid mathematical formalization, something that other physicists can pick up, work with, critique, and use to make precise calculations. It needs to be testable quantitatively.
Peer review, mathematical rigor.
Exactly. And finally, it just takes time for the wider scientific community to engage with it, replicate findings, debate it, and eventually, if the evidence holds up, integrate it into the mainstream understanding.
There's that great Einstein quote, isn't there? Something like, if at first the idea is not absurd, then there is no hope for it.
Yes, that captures it perfectly. Truly novel ideas often seem completely outlandish when you first encounter them because they break from ingrained assumptions.
Does motion theory feel absurd enough in that sense?
I'd say so. The idea that solid matter, gravity, everything is just structured rhythmic motion, it's definitely audacious, it's counterintuitive. But as we've discussed, it also seems to offer this, surprising internal coherence and potential explanatory power. So yes, it perhaps fits Einstein's criterion of productive absurdity.
So we can't sit here and say the person behind motion theory is the next Newton or Einstein. That's not the point, and history will decide anyway.
Exactly. That's for time and evidence to determine.
But what's the takeaway for us, for you listening? What's the significance of considering this theory now?
I think the key takeaway is that motion theory, regardless of its ultimate fate, represents a serious attempt at a profound unification. Its potential implications are huge, its explanations for some tricky problems are elegant, and there's some preliminary evidence that warrants attention.
So it deserves serious consideration, serious investigation.
Yes. The focus really shouldn't be on labeling the creator, but on grappling with the idea itself. Could reality fundamentally be about structured motion and synchronization? What would that mean?
It shifts the focus to the potential transformation of our understanding, like those earlier revolutions did.
Precisely. And that leads to the final thought, really, for you, the listener. The best thing you can do with a radical idea like this is engage with it critically.
Discuss it, debate it.
Question its assumptions. That's how science moves forward, especially revolutionary science. So think about your own experience. The feeling of solidity, the passage of time, gravity holding you down.
Could you reinterpret those through this lens of structured rhythmic motion?
Maybe. What parts of this idea resonate? What parts seem completely off the wall or, yes, absurd? Mull it over. That process of questioning is the scientific adventure.